So quiz one on the books. Overall, I think we did pretty well. Hopefully it fits within what you were expecting. I hopefully didn't catch too many of you off guard. And I very much hope that several of you saw questions on there where you're like, wait a minute, I've seen that exact question because I took them from the homework. I'm not always going to do that, but I will occasionally do that to again encourage you to do the homework. I don't grade the homework, but it is an excellent practice. If you went through all of the Action Center as much as you could and all the homework and still feel like the quiz was like, hey, wait, what's going on here? Let's chat and figure out where the holes are. Because probably what's going on is we're not setting the threshold high enough in our brain about, do I actually know this? Did I complete the problem or do I understand the problem? I need you to get to the understanding part so you can apply it to other problems. Overall, I think we're doing great. Keep in mind that there's lots of quizzes in here, plus you get a dropped quiz, right? So, and then the other thing is the 85, 75, 65 split. 85 and above is an A, 75 and above is a B, 65 and above is a C. Any questions for me? Did everybody see the key get posted? Okay, and then the key for Action Center also got posted. Those are all on Blackboard. A couple of us are still having a hard time getting a hold of Blackboard. Today, immediately after class, is a great time to solve that so we can all see all the stuff that I'm putting on the board. Outside of that, let's talk about chapter 2. If you thought chapter 1 was fun, and I know you did, you're going to love chapter 2. Because chapter 2 is when we kick it up a notch. We talked about homoatom bonds, so hydrogen bonding to hydrogen, carbon binding to carbon. What happens when a carbon makes a bond to hydrogen or when an oxygen makes a bond to hydrogen? That leads to something called polar covalent bonds. Good morning. And then because they didn't have a better place to put it, we're also going to talk about acids and bases at the end. But it's kind of like its own section. That should really be like chapter 2.5. All right, first thing up here, polar covalent bonds. What are they? A polar covalent bond is when bonding electrons are shared unevenly. Between two atoms. You can tell from all of your faces right now, you're wondering, but Dr. Green, why? Why would two atoms share electrons unevenly? There is a component, there is an identity for each atom called what? About how it pulls on electron density. Yeah. Electronegativity, that is correct. That is a positive answer. Electronegativity is the root of most chemistry, this uneven sharing of electrons. Electronegativity. That is a big long word, so you're going to see me abbreviate it EN. Electronegativity is the ability of an atom to attract shared electrons in a covalent bond. Sorry about all the definitions here to start. I will start drawing pictures soon. We've been talking about bonds like handshakes. And so when I talk about a handshake, it's normally a handshake is like, hey, nice to meet you. You reach out, we shake hands. This is like a really rude, awkward handshake where you go, hey, it's very nice to meet you. And then the other person goes, very nice to meet you too, and pulls you towards them, right? Unwelcome handshake. That's electronegativity. One of the people on that handshake is too strong. They are roided out and they're like, "Grr," right, pulling all the electronegativity towards themselves. Why are they so crazy? There's two good reasons for electronegativity differences. Good morning. One is called effective nuclear charge. Now, this is going to get confusing because I'm going to define electronegativity, or I'm going to represent electronegativity as En. One of the components of electronegativity is effective nuclear charge. Guess what I'm going to use for that? ENC. It's super annoying. I didn't come up with this rule. We'll put it in lowercase just to make it a little bit easier, but normally you'll see it as ENC like this. So ENC is one of the contributing factors to En. Again, my apologies. The other factor here is atomic size. Let's talk about these one at a time here. The first one up is the effective nuclear charge, or the ENC. You know what? That looks really weird, lowercase. Let's just keep it. I'm going to just abandon that right now. I already don't like it. Occasionally you see people use it lowercase. Let's just keep it all uppercase. All right, the effective nuclear charge is how much the electrons feel the nucleus. I like to think of effective nuclear charge kind of like a campfire. Let me show you a couple atoms and then we'll bring up this analogy here. I'm going to compare carbon to oxygen. In the middle of carbon is a nucleus. How many protons are in that nucleus? 6. So I'm going to put a +6 here. Oxygen has a nucleus with how many protons? 8. How'd you smarties know that? Why are you looking around? It's on the periodic table, right? The atomic number tells you how many protons are present. Oxygen has a +8. I always want to make like nerdy D&D references here. +8 to positive charge. Roll the dice. A couple of you know what I'm talking about. The rest of you, you should see that movie that they just came out with for Dungeons and Dragons. So funny. Good stuff. Carbon has 2 shells of electrons around the outside of it. This one has 2 electrons. Where do they sit, nerds? Like, well, I'm not going to answer now. You're being rude. 1s. So the first 2 electrons are in the 1s orbital. And then in the second shell, note to self, Dr. Green can't draw circles. Really can't draw circles. First try. The second shell has how many electrons in it? 4. Better have 4, otherwise carbon has a charge. So 2 electrons plus 4 electrons makes 6 electrons. 6 electrons balances out the +6 in the middle here. What do I call these electrons? Valence electrons. Right? It doesn't matter how many are there. It's the fact that they're on the outside. And just as a quick reminder, where are those 4 electrons? There's actually 2 answers here. What orbital do those electrons sit in? Which orbitals do those electrons sit in? 2s and 2p. So the full electron configuration here is 1s2, meaning 2 electrons in the first shell. 2s2, meaning 2 electrons in the second s orbital. And 2p2, 2 electrons in the p orbital. Va bene. How about for oxygen? It's got the first shell here. What is that? Same thing, 2 electrons. They sit in the 1s orbital. How many electrons in the valence? 6, because 2 plus something must equal 8, and that something is 6 electrons. So I just drew the electron configuration without the S and P in there for carbon versus oxygen. Let's come back to our campfire example. Let's pretend this is, this will be fun. This is actually playable, right? So this is my campfire. If it's carbon, That'd be really hard. I should go borrow. I bet they have something that I can sell on fire. If this is my carbon campfire, it is +6 campfire. Right? So my +6 campfire is 6 warm. In the first shell surrounding this, there are 2 folks standing here warming their hands. But I'm worried about the valence electron. So I'm actually back here. So when I go to warm my hands in this fire, do I feel +6? No, because there's some people standing in my way. This is where I want to be, right? This is the nice spot. I'm in the first shell, I get to feel all +6 of that. If I'm in the second shell, I have to worry about 2 electrons screening out some of that charge. So I don't feel +6. What do I feel? Okay. +4. Because what's happening is this positive charge that's radiating out from the center of this atom is being screened by 2-, which means the carbon valence electrons feel +4. Carbon has an effective nuclear charge of +4. Same story. Now we have oxygen. Oxygen's got even, I guess that's kind of a bigger fire, right? Okay, so now my middle fire here is a +8. I got 2 folks around here warming their hands. I'm in the valence. I have 6 friends with me, but it doesn't matter. I'm in the valence electron. I'm gonna warm my hands. What do I feel? +6. So I don't feel all +8 of it. I feel +6. Oxygen has an effective nuclear charge of +6. So who cares? You care, and electrons care quite a bit. If I'm a valence electron in an oxygen, I feel more of the nucleus, which means I go, actually get a little bit closer to this fire. I'm still in the second shell, but I'm going to just get a little bit closer because I feel more of that warmth, and that makes me really happy. If I'm in a carbon, I don't feel as much of that middle charge, and so I'm like, well, this would be nice, but there's nothing really pulling me into it. This greater effective nuclear charge means that oxygen can pull electron density in towards itself. It has more of an attractive force because its campfire in the middle, its nucleus, burns hotter than other nuclei. Probably write that down somewhere, but does that make sense? Ish. Okay. So if carbon and oxygen form a bond, carbon's on one side, oxygen's on the other side, they reach out and shake hands. Oxygen is going to say, give me that electron density. Because, well, actually, the electrons are going to be more attracted to the oxygen because the oxygen has more to offer it in its nucleus. That means the bond is going to get pulled towards the oxygen and lead to something called the dipole moment, but we'll get to that in a second. Effective nuclear charge increases as we go from left to right. If you look at the periodic table, really the side we're concerned about here is boron, carbon, nitrogen, oxygen, fluorine. As we go this way, we go from an ENC of 3 on boron to 4 to 5 to 6 to 7 on fluorine. So I am increasing effective nuclear charge. If oxygen and fluorine make a bond, who wins? Fluorine. If nitrogen and oxygen make a bond, who wins? Oxygen. So we're just getting increasingly better at pulling electron density as we go to the right-hand side of the periodic table. That is one factor of electronegativity. The other factor is atomic size. So when I was talking about kind of warming my hands near this fire here, I was really dealing with 2 shells because boron, carbon, nitrogen, oxygen, and fluorine, their valence electrons are here. They're all approximately here. And actually, speaking of size, they're about the same size, but actually, as you go from left to right across the periodic table, atoms get just a little bit smaller. They contract because of effective nuclear charge. I'm in the second shell, but if I'm in oxygen, I go, that's not sense. So as I lean in, the oxygen radius decreases a little bit. As I go down the periodic table, I'm really increasing the size or decreasing the size of the atom. So if I'm in oxygen, I'm in the second shell. If I'm in sulfur, I'm in the third shell. Right? And as I go down the periodic table, I just get farther and farther out from this thing. That has a big impact on how attractive electrons are. So our second factor here is size. So let's compare carbon to silicon. Carbon has a +6. For those of you on the wings, how many protons in the middle of silicon? 14. Now, why am I choosing carbon and silicon? Where do you find silicon? Directly underneath carbon, right? So I don't want to go left or right on the periodic table. I'm just saying carbon sits here. You go down one, silicon's right there. So no left and right, just down. Let's build out our electron configuration for carbon. It has 2 shells. So 2 electrons there, 4 electrons there, same story. Silicon has 3 shells. You can put 2 electrons in the first. How many total electrons can go in the second? 8, very good, the octet rule. Which leaves me how many electrons in the outer shell? 4, because I need to add up to 14. 8 plus 2 is 10. I better have 4 more electrons here in the outermost shell. If you're an electron, a valence electron, do you want to be on carbon or do you want to be on silicon? You want to be on carbon, right? So there's my campfire. You can either be here or here. I want to be here. Carbon is more electronegative than silicon because carbon's electrons are closer to the nucleus. Does carbon or silicon have a greater effective nuclear charge? They're the same. Dr. Green's mean. How do I know that? So I have a +6 charge here. 2 of it's going to be filtered out by the inner electrons. So I have an effective nuclear charge of +4. I got to do the same thing over here. What do my valence electrons feel? What is the effective charge that reaches the valence electrons? And remember, we're worried about valence electrons because those are the electrons that make bonds stuff, right? So my valence electrons out here are screened by 10 electrons in the middle. +14 radiates from the nucleus. 10 of that +14 gets filtered out. So only +4 makes it to the other side. Silicon also has an effective nuclear charge of +4. So if I ask you which one of these atoms, carbon or silicon, is more electronegative, you would say carbon is more electronegative. And then because I'm super annoying, I would say, why? And the answer to that would be carbon has a smaller atomic radius. The answer would not be carbon has a greater effective nuclear charge because they have the same effective nuclear charge. And in fact, silicon and carbon have a lot in common. Carbon makes 4 bonds, pretty strong. Silicon makes 4 bonds, pretty strong. We call silicon-based structures typically silicates. So silicon and oxygen make really strong bonds. It is the basis for most rocks. But if the rocks got hot enough, you can turn rocks into liquid. And so really what you need for carbon to make life is carbon makes 4 bonds and it also forms really flexible molecules like DNA. So if there was a really hot planet somewhere that was all molten silicon, there's probably rock people that exist somewhere because silicon makes all the same number of bonds that carbon does. So you can make silicon-based DNA. So if you're a Trekkie, which maybe 1 or 2 of you in here are, they have these like rock civilizations of people that like are made out of quartz and stuff. That's real. I'm positive of it. They just wouldn't be rocks. They would be like molten lava people. Please don't tell me you have a question about that and something about actual chemistry.
So carbon is smaller atomic radius because it has like less. So
Correct. Carbon has two shells of electrons. Silicon has 3. So as we go from top to bottom here, so carbon, silicon, germanium, so on and so forth. As we go this way, we have a larger atomic radius. So what happens to our electronegativity as we go down the periodic table. It gets worse. Yeah. Yeah, that's rude. So I'm not going to go diagonal for you because it gets mean unless you're going diagonal in a particular direction. So if we go, you're leading me here. Love it. Pretty good looking periodic table. I know. If we go this way, diagonally up to the right, what's happening? Increasing electronegativity. Why? Because we go from left to right, we are increasing the effective nuclear charge. And as we go from bottom to top, we are decreasing atomic size. So the all-time winner and losers on the periodic table, fluorine. Is the most electronegative atom on the periodic table. And poor francium over here in the corner is the least electronegative. This would have been cuter and funnier if I gave myself more space. Now it's just cramped in there. Francium is the least electronegative atom on the periodic table. Fluorine is the most electronegative atom on the periodic table. And if you squint at that periodic table, you may notice that fluorine is not the highest to the right. And which one is? Helium. Why is helium not the most electronegative atom on the periodic table? Because helium does not make covalent bonds to things. We talked about if helium tries to make a covalent bond to something, its electrons are as benefited as they are hurt. And so it just tends to fall back apart. It is a noble gas. Electronegativity is defined by the ability of an atom to share electrons in a covalent bond. Helium and all of the noble gases do not make covalent bonds, so they don't get to play in the electronegativity sandbox. That makes sense? Yeah. Yeah. So if you go diagonally left to top to bottom to the right, it's complicated. So some of the atoms, we can measure electronegativity in terms of debye, but it's tough. I'm not going to have you do that. So I will either make it clear, I'll have you move laterally just across effective nuclear charge or down a column using atomic size, or I'll go diagonally up and to the right. Otherwise, it's something you'd look up. I believe carbon is more electronegative than phosphorus, but there is a nuanced conversation there because carbon does not have as great of effective nuclear charge, but it has a smaller atomic radius. So you have to you're in gray area there. Good question. Others? Okay. When atoms do this, I'm going to write this. I'm kind of doing this a little bit backwards, but it's okay. Atoms that form covalent bonds with different electronegativities lead to. No, I don't want to do that. This leads to something called the inductive effect. The inductive effect is the uneven sharing of electrons across a sigma bond. So this is the handshake I'm talking about. When electrons interact with each other head on between nuclei, if one of the atoms is more electronegative, it pulls harder on that bond. So it's kind of like tug of war. You pull on the rope harder, you move that electron density towards yourself, but specifically through a sigma bond. We're going to talk about other ways to move electron density around through pi bonds and other mechanisms. But if it's through a sigma bond, that leads to something called the inductive effect. The inductive effect leads to a dipole moment. So many definitions. The dipole moment is the measure of charge at one end of a molecule compared to the other, or measure. Yeah. Measure of charge across a molecule. So when carbon and oxygen form a bond, a sigma bond, they aren't going to share the electrons evenly. Who's going to win the fight? Oxygen is going to win the fight. So when carbon reaches out for a handshake, oxygen is going to do the awkward thing where it pulls carbon too close, stealing its electron density. Why is oxygen going to win that fight? Why is oxygen more electronegative? Nah, let's get like real specific here. Why specifically is oxygen more electronegative than carbon? Oxygen has a higher effective nuclear charge than carbon. They are basically the same size. Oxygen's actually a little bit smaller, but effectively the same size. Oxygen's greater effective nuclear charge means oxygen is more electronegative. Oxygen being more electronegative means it's going to pull the bond towards itself, which is going to create a dipole moment. We show dipole moments with arrows. This is a dipole arrow. I put a little cross here on the end, so it kind of makes like a plus sign. A dipole arrow points from the atom that's being robbed to where the electrons are pointing towards, in this case, the oxygen. These little dipole arrows are super important because they're going to lead to electron imbalances that lead to all reactivity that we're going to talk about. When one molecule reacts with another molecule, it's going to be because one molecule is electron rich and the other one's electron poor. And to figure out who's got electrons and who wants them, we're going to use these arrows to get to that first principle. Let me show you a couple examples of these. But before I do that, any questions on any of this stuff? A little bit of Gen Chem review. Does this look familiar to us-ish? Or, yes, I've heard this and I promised myself I'd forget it then and I kept that promise because I don't remember it now. Guilty. I was not a fan of Gen Chem. I was bad at it and it just like didn't work for me very well. It was just like, I was like, okay, I got this concept. I worked really hard on it. Wait, we're talking about something else now. Great. Okay. I don't know what you're talking about here. Okay, but I got it. Wait, no, you're going. Ah. And then we got into organic and we were like, let's spend the whole semester talking about carbon. And I was like, that's my jam. Let's do this thing. Yeah.
So does the effective nuclear charge always line up with the number of electrons it has?
Does the effective nuclear charge always line up with the number of valence electrons it has? In a neutral atom, yes. In a neutral atom. Now in charges, it gets crazy, but yeah. No, you're good. You can take the one more time. Yep. Yes, I think that's practically going to be difficult for you to do. So at that point, you're kind of drawing out the electron configuration either way. I think what Peyton's looking at is how can I use the periodic table to get to the shortcut here? Right. So the valence electrons for carbon are 4. It has an effective nuclear charge of 4. Nitrogen has 5 valence electrons. It has, let me double check myself here before I lie to you all. Nitrogen has +7 in the middle, right? So it's got 2 electrons here, which means it has 5 electrons here. The 5 electrons feel +5. Nitrogen has a +5 effective nuclear charge. And so I think what you're doing, right, is wanting to get to a shortcut of how you get to those effective nuclear charges. I still build it out each time because it helps remind me of like what we're even talking about here. Otherwise, it's just another number. But yeah, I'll get you there. Good questions. Others?
So 2 electrons and 5 electrons available to the outside. What are the 2 electrons in the inner orbital moving in?
That's just where they are. So there's a 1s orbital. You can put a maximum of 2 electrons in it. When it's full, then you have to go to the second shell. Shouldn't have erased that last screen. Others? Good to hear from you guys. You may have picked up on this, but I can just so you have to ask questions, or I just keep going. Start talking about rock people in Star Trek. Let's talk about a couple different molecules and see if we can't come up with some dipole moments. This is water. Does water have any polar covalent bonds in it? Oh yeah. Between, say, hydrogen and oxygen. Which one of these is more electronegative? Oxygen is much more electronegative. Now, hydrogen is smaller. And then, actually, I need to show you this real quick. So on the periodic table, boron, carbon, nitrogen, oxygen, fluorine, up. All right, so hydrogen's actually over here on the periodic table. Yeah, but it's actually over there because it only has 1 electron. Mendeleev put the periodic table together based on the nuclei and electrons. He did this without electricity, by the way, so much smarter than I could ever possibly be. A lot of chemistry was figured out by candlelight, which blows my mind. Hydrogen's electronegativity actually sits right about here. It is slightly less electronegative than carbon, but much less electronegative than oxygen. So functionally, think of hydrogen, effectively being right on top of carbon, just a little less of an effective nuclear charge. So because of that, I'm going to draw a dipole moment from the hydrogen to the oxygen. Put my little cross arrow back here, meaning hydrogen's being robbed, oxygen's gaining the electron density. Are there any other dipole moments in this molecule? Other way, right? From that hydrogen to that oxygen. All right, we got to do a little bit more math, but the good news is this isn't numbers math, this is arrow math, so vector addition. Vector addition is the process of adding up arrows. Vectors can have both a direction and a magnitude. If I was going to go from this side of the screen to that side of the screen, and I was like, here we go, I'm going to make it over there, this is great. I could represent that motion with an arrow that looks like this. I went from this side to that side, but I didn't do it very fast. On the other hand, I started over here and I was like, okay, here we go. I went to that side. I traveled the same direction, but it looked like an idiot doing it because my arrow now looks like this, right? I traveled much faster going that direction. The size of the arrow represents the magnitude. The direction of the arrow represents the direction. So these arrows are going to add together, but you need to consider the size of the arrows as you're adding them up. I have one arrow that's pointing this way, one arrow pointing this way. They are equal in magnitude, which means they're going to combine to make an arrow that faces straight up. This is what we would call a molecular dipole. If a molecule has a molecular dipole, the molecule is said to be polar. Water is a polar molecule because the bonds between oxygen and hydrogen are polarized, because oxygen has a greater effective nuclear charge. And this is what I freaking love about this class. We all know water is polar, right? We've always talked about water's polar, oil is non-polar, they don't mix, right? We are going to take everything in this class back down to these first principles. Why is water polar? Because it doesn't share electrons evenly. Why doesn't it share electrons evenly? It comes down to the nucleus and the attraction of the electrons. I find that greatly intellectually satisfying. I'm sure you do too. How about methane? Are there dipole arrows in methane? Yeah. There is a carbon-hydrogen bond. Which one of those is more electronegative, carbon or hydrogen? Carbon is. Should I draw an arrow that's the same size over here? because the electronegativity differences between carbon and hydrogen are very small. So I'm going to represent that by an arrow that's pointing this way, but itty bitty. Because there's not a big pull between the carbon and hydrogen. It's like a little bit of like an aggressive business handshake. You go to shake their hand, someone's like, a little bit, and you're like, well, you're trying to like tell me something. It's not a full-on bear hug, but it's there. Every one of these carbon hydrogen bonds does that, all to the same order. Does methane have a molecular dipole moment? No, it does not. And this is the thing we love to torture you about in Gen Chem, where we use geometry to mess with you. And we say, hey, can you identify the bond dipoles? And you're very good at that. But then do you recognize that the bond dipoles exist in a three-dimensional structure? That's the harder challenge here. Remember that methane, the carbon in methane is what hybridization? sp3, and the bond angle of an sp3 hybridized carbon is 109.5, which gives it a structure of a tetrahedron, full points. Tetrahedrons are three-dimensional structures. So the bottom hydrogens all have arrows that are pointing up. The top hydrogen has an arrow that's pointing down. So three little arrows pointing up, kind of like that, and one arrow pointing down. They cancel each other out. Same thing to the left, same thing to the right. All the arrows that add up in one direction are countered directly by another arrow facing the opposite direction. There are bond dipoles in methane, but there is no molecular dipole in methane because they cancel each other out. Gunnar. Tetrahedral is a way of using it as an adjective. Tetrahedron is a noun. ON. So methane as a unit is a tetrahedron. That is a shape. That carbon in methane is tetrahedral. It's part of the shape that makes up a tetrahedron. You'll see hedral used more often because they're going to be carbons of a more complicated structure. Methane is a tetrahedron because it's actually balanced. Most carbons aren't strictly tetrahedrons because they have different things attached to them. But the carbons themselves are tetrahedral, meaning the bond angles are 109.5.
So is that specific one that it's like more
Correct. So this is a tetrahedron. This is more of a geometry. This is not super important, but this is a tetrahedron because everything's balanced around the outside. I put an OH up here. Now the carbon is tetrahedral, but the structure isn't a tetrahedron anymore because it's lopsided on one side. We're going to get philosophical real fast if we haven't already become that. Let's do one more. And you guys do it. I'm talking too much up here. This molecule is, let's be super annoying about it. Carbon dioxide, CO2. I want you to draw a Lewis dot structure and then a line structure. And then tell me if there's any bond dipoles and tell me if there's any molecular dipoles. I almost drew the structure out there. That was a missed opportunity. How many valence electrons do I have to play with? What was that? 16. Okay. So I have 12 from the oxygens, 4 from the carbon. How do I get those numbers again real quick? Periodic table. So the 6, Roman numeral 6 above oxygen lets me know that I have 2 of them, 12. That is 16. Anybody draw a structure out? Who have I not heard from? Caleb, what are you drawing over there? OO on either side. What's the nature of the bond between the OO? Double bonds, very good. So if I put a double bond there and a double bond there, that's 2, 4, 6, 8. 10, 12, 14, 16. Octet around the oxygen, octet around the carbon, octet around that oxygen. Very nice. This is carbon dioxide. Where do you find carbon dioxide? Which made a bunch for you just now. You're making some as well. Carbon dioxide, does it have bond dipoles in it? Yeah, what are they? From the carbon to the oxygen. All right, so if I'm keeping track of this, I had a big bond dipole over here. I had a small bond dipole over here. How about this one? And in the middle, right? So since they're all on the same page, I'm going to draw an arrow that's like maybe a little bit longer. It's not as long as that. It's definitely longer than that. So I'm using my arrows here to represent how big is that indifferent, or how big is that difference in sharing. Promise, last time I'm going to ask, why am I drawing arrows from the carbon to the oxygen? Peyton. Because oxygen is more electronegative, and just because you know it's coming, why does oxygen have a greater, I almost said it. Why does oxygen have a greater electronegativity? Because it has a greater effective nuclear charge. You have a quiz on like Tuesday, I think. Anyway, things I'm thinking about. Does carbon dioxide have a molecular dipole moment? No, it does not. The carbon or the oxygen that's pulling this way is canceled out perfectly by the carbon by the oxygen pulling that way. So one gets pulled that way, one gets pulled this way. They cancel each other out, and there is no molecular dipole here. You don't need to know this, but carbon dioxide. Oh, sorry. Yeah. That's a good question. What is the hybridization of that carbon? Love it. There's no triple bond there, right? So if you see double bonds, your shortcut is, oh, there's double bonds, it must be sp2 hybridized. How many electron domains does that carbon have? 2, which means that carbon is what? sp hybridized. And the bond angle around an sp hybridized carbon is 180 degrees. So this molecule is linear. So there's no triple bond here. It's a double bond on one side, a double bond on the other side. So what's happening is I've got a p orbital facing up and down, making a pi bond that way. And I've got a p orbital coming in and out of the page, making a pi bond that way. They are opposite each other, but they're not on the same carbon oxygen bond.
So the sp orbital can either double
No, it's not the sp orbital that makes that. Remember, a triple bond is 1 sigma and 2 pi's. So that's what this carbon's doing. It's making a sigma bond that way and a sigma bond that way, a pi bond that way and a pi bond that way. So it's using an sp orbital to make a sigma bond that way. It's using an sp orbital to make a sigma bond that way. Using one of its p orbitals to make a pi bond that way, and the other p orbital to make a pi bond that way. Using all the same orbitals, just in a different configuration, how we've seen before. Excellent question. Maybe a little more advanced than I want us to be right now, but I'm glad you're thinking about where are those electrons. In Action Center on whatever day it was, Monday, Tuesday, whenever we met, we were talking about decaf coffee. Carbon dioxide plays a pretty important role in decaffeinated coffee. You can take carbon dioxide, which is a gas, right? It's made some more. And if you squeeze it enough, you can turn it into what's called supercritical fluid. So gas is defined by the principle that it fills up whatever volume you put it into. So I don't want to gross you out, but when I go, my carbon dioxide breath is going to fill up the entire room, just like yours is. But if I pressurize this room, I could get all the carbon dioxide in here, kind of settle out into the floor a little bit. Not like a liquid entirely, it's still a gas, but it kind of flows like a liquid. Because it is nonpolar, we can get nonpolar things to dissolve in it. So when you commercially decaffeinate coffee, what you do is you take your big batch of beans, unroasted, by the way, put them here, you put a bunch of supercritical CO2 on top of it. So you put them in a pressure chamber, blow in carbon dioxide. The carbon dioxide settles on top of the beans. When you blow that carbon dioxide off, it carries with it a majority of the nonpolar material in the coffee beans. Caffeine, an alkaloid, is fairly nonpolar. It actually doesn't dissolve that well into water. That's why we have to brew coffee and tea hot if you want to get the caffeine out of it. We'll talk more about that in a while. So if you blow the carbon dioxide off of the coffee and then remove the pressure, what you would get is a big pile of caffeine. So if you like energy drinks, same process. We get a lot of our caffeine by taking the caffeine out of coffee, using carbon dioxide as a gas, remove the carbon dioxide gas, you have a big pile of caffeine. You can then go put that in energy drinks. And the coffee that's left behind has all the delicious things that make coffee taste good, but without the caffeine associated with it. Why would you want to do all this process of using carbon dioxide when you could just use an organic solvent? Think of some organic solvents that you may have heard of. Gasoline is one of them. You want to drink coffee that's been soaked in gasoline? No. Dichloromethane is another one. Ether is another one. If you're not familiar with these solvents, but you're taking lab, you will be familiar with them. And I promise you, when you smell them, the first thing is not going to come to your mind is, ooh, I wish this was in my coffee. A lot of organic solvents are really gross. They are actually really toxic for us. Carbon dioxide is, of course, in large concentrations bad for us, but it's harmless, right? It just blows away. So this is a really human-friendly thing to be able to work with to move nonpolar materials from foods. And decaffeinating coffee is one of the most common applications for that. You don't need to know any of that, but I think it's super interesting. If you ever see a video of it, it's pretty cool. Supercritical CO2, whatever. Yeah.
So, in order for something to be polar and non-polar, the dipolar, the moments have to be canceled out.
Right.
So why is water non-polar if both of them cancel?
Water's very polar.
Yeah, so why would they be not polar?
Because these two don't point directly at each other. Water is not linear, right? If the water was linear, it would cancel out. Water is bent, which means the two arrows add up to an arrow pointing straight up. This is where the molecular geometry really matters. And this is why when we were talking about hybridization, why I had you memorize bond angles, this is one of the reasons why it's so important. This carbon being tetrahedral and this carbon being linear have a big impact on their polarities. If this carbon was not linear, carbon dioxide would have a dipole moment. Then you would not be able to decaffeinate coffee with it. But the fact that it's linear gives us that property. The more you know. All right, I have had you draw structures here for a little while using some really rudimentary rules, mainly just the octet rule, saying draw something and don't break the octet rule. We need to be a little more civilized, and I need to give you some more tools for assessing your structures. The most important of those tools is called formal charge. Formal charge is the electron bookkeeping where we're going to measure associated electrons versus total electrons. Our associated electrons are counted by adding up all the lone pairs and half the bonding pairs. My wife and I are playing through the new Zelda game right now. I don't know if anybody else is playing Tears of the Kingdom. That game is gorgeous. But if you've ever played Zelda, you know that all the important stuff's always like in red, like drab language, and then red, that's the thing, go find the Master Sword. I want you to focus on lone pairs and bonding pairs here. We're going to differentiate those when we're adding up electrons for different elements. Let me show you this, I think, on a molecule instead of like trying to talk more through it and see if this makes sense. First example we'll use is methane. And again, I keep going back to methane here because this is an organic chemistry class and methane is the simplest organic molecule. Methane has a formula of CH4. So when we do all our, you know the structure of this because I just drew it, but let's do it de novo each time. Carbon's going to bring 4 electrons. Each of the hydrogens brings 1. So we have 4 there for a total of 8 electrons. Those electrons, when they're in shared pairs, are divvied up between the atoms. The carbon gets to claim 4 of those electrons. The hydrogen gets to claim 1. So there's like a marriage of sorts going on between the carbon and hydrogen. If I break that couple up, the hydrogen's taking one of the electrons back with it. It's like, hey, I brought this electron with me. You don't get to keep my electron. Even though you're more electronegative, I get half the bonding pairs here. So we would say that carbon has 4 associated electrons. And I'm going to keep putting this in quotes. That's just a phrase I'm using. Yes, there are 8 total electrons around the carbon. It has an octet. But carbon at the end of the day only gets to count 4 in its individual piggy bank because it's sharing 4 of the other electrons with hydrogen. We can use that number to figure out if carbon has a charge or not. So what we're going to do is compare the number of electrons it has associated with it to how many electrons it should have according to the periodic table. I'm going to show you this as a mathematical formula, which maybe works for a couple of you. And I'm going to show you how I do it, which is just to count with your fingers because I'm simple and I like to count with my fingers. Formal charge. Let me write it down over here so it's nice and big. Formal charge, also called FC, or some people also use Z, is equal to the number of valence electrons in the free atom I really hope that's not part of the demonstration there, the screaming child, minus the number of associated electrons. The associated electrons over here are going to be the number of bonding electrons divided by 2, because each of those electrons are shared, pairs of electrons, plus the number of non-bonding electrons. The whole thing over here is the associated electrons. I do not much care for this equation. Some students really like it. If you don't much care for this equation, we're in the same boat. If you like the equation, good for you, use the equation. Here's how I calculate formal charge. I'm going to go over to carbon and say, how many electrons should carbon have? Look at the periodic table and say, in the free atom, carbon should have 4 associated electrons, right? The periodic table tells me find 4 electrons. I'm then going to go to the bond and I'm going to count. Let me draw it out actually as a full line structure here. I'm trying to figure out how many associated electrons carbon has. It doesn't have any lone pairs, but I'm going to count up its bonding pairs in half and say it has 1, 2, 3, 4. Carbon has 4 associated electrons with it. It wants 4 associated electrons. Carbon has a formal charge of 0. The electrons it wants, it has. So it has no formal charge. The mathematical way of doing this is saying this number is 4 minus 8 divided by 2, right? Because the number of bonding electrons is 2, 4, 6, 8 divided by 2 plus 0. So 4 minus 8 divided by 2, which is 4 minus 4, formal charge of 0. I'm not going to do this anymore. I'm going to calculate all the other formal charges I'm about to show you by just counting up the number of bonds and lone pairs around an atom. You're giving me a confused look right now, so let me show you some more examples of this, and I promise it'll make sense when I do that. Questions about that formula as written before I really tell you how to do this? Yeah.
So the 3 atom means
Neutral atom. Yeah. Non-bonded atom. That'd be a good note to put in here in the neutral. Free neutral atom. Let me show you a few different molecules here that you've already seen before, but I'll show you how we know that they are either neutral or have a charge. So water. I'll write all these down first. Ammonia and methoxide. So water has a formula that looks like, it has a structure that looks like this. I want to know the formal charge of oxygen. So first thing I need to know is how many electrons is oxygen expecting to have in this relationship? How many electrons should a neutral oxygen have? 6. Periodic table tells us we're looking for 6 electrons. Let's figure out how many electrons this oxygen actually has. I'm going to count all the lone pairs. So 2, 4, 5, half the bond, 6, half the bond. Now the marks I'm putting on here are how I count it. If you watch me do this on paper, I literally am making those pen strokes. I'm just not making any marks on there. I would go, okay, Nathan, don't screw this up. I'm looking for 6 electrons. To this day, I still like swipe my pen across bonds and just count 1, 2 that way. You see how I counted that? Half the bonds, 1, 2, all the lone pairs, 3, 4, 5, 6. Oxygen wants 6, it has 6. Oxygen has a formal charge of 0. And when an atom has a formal charge of 0, we just don't write anything for it. That makes sense? You guys do ammonia. Yes, there are dashes and wedges here. No, I'm not going to put them because that's not what we're focused on right now. What's the formal charge of nitrogen? What is it? What? Loud and proud, dare to be wrong. How many valence electrons should nitrogen? 5. So we're looking for 5 associated electrons for that nitrogen. I'm gonna stay with me. How many associated electrons does that nitrogen? 5. It's 1, right? What 1 just did is she looked at this nitrogen and said, I'm looking for 5 electrons. She counted 1, 2, 3, 4, 5. All the lone pairs, half the bonds. The nitrogen wants 5 electrons. It has 5 electrons. There is no formal charge on that nitrogen. Do one more. I'm going to draw this one out for you. What is the formal charge, if any, of that oxygen? a lot of hand gesturing here. How many associated electrons are we shooting for here? Emily, how many associated electrons does this thing have? 7. It has. Every time it's on the board, I always want to reach for it. And I'm always like, I can make it. And 1, 2. It has 1, 2, 3, 4, 5, 6, 7. This oxygen has 7 associated electrons. It only asked for 6 electrons. You just gave it 1 more electron than what it should have. What is the charge of an electron? Negative. Electrons are negative, and this oxygen has 1 too many, so that oxygen has a -1 charge. You would say a formal charge of -1, or if you want to be really cool and write really fast, you just give it a negative with the circle. If you want to do this mathematically to get to this, you would say the formal charge of that oxygen is equal to the number of valence electrons it should have in the free atom, which is 6, minus its associated electrons. It has 2 divided by 2, so a bond over here, plus 1, 2, 3, 4, 5, 6 non-bonding electrons. 2 divided by 2 is 1, 6 plus 1 is 7, 6 minus 7 is -1. I never calculate formal charge this way, but some of you are mathematically inclined and you feel free to do it. You're going to see me count it out by hand each time because that's just how I roll. Either way, whatever works for you. I recommend just doing one, not trying to do both all the time because you'll tie yourself in a pretzel. Questions about formal charge? That make sense? Yeah.
One more than needs minus.
If it has 1 more than it needs, you need to remember what it has 1 more of. It has 1 more electron than it needs, and electrons are negatively charged, so it has a minus. What do you think if it's missing an electron that it should have?
Plus.
It'd be a +1. How do you think methoxide, this molecule is called methoxide, how do you think methoxide feels about having that negative charge? Bad. Oxygen is very electronegative. It can hang on to negative charges pretty well, but oxygen would much rather be neutral. Putting a charge on a molecule is a burden. It raises the energy. There are too many electrons around that oxygen, is what we're saying. So what does a poor molecule do when it has too much electron density or not enough electron density? It does what all other molecules do, and it finds other ways to try and share that electron density, which is my excellent segue into section 2.4, which is resonance structures. Resonance structures are different structures of a single molecule. That are formed by relocating pi bonds and non-bonding electrons. Non-bonding. I like to think of resonance forms. Well, actually, I need to stop doing this. I'm going to tell you the chemistry first and then use my weird analogy because I think cart before the horse is just confusing the crap out of all of you. Let me show you resonance forms in a molecule, and then I'll get to my dumb example. If we're going to move pi bonds and lone pairs, the molecules have to be a little more complicated. Methoxide has lone pairs, but it doesn't have any pi bonds. So I actually can't resonate anything here. I'm going to draw a sufficiently more complicated molecule. And a quick note, I am spoiling you all. I am still drawing Kekule structures. Remember, I could draw this structure like that. I'm not doing that yet, but I need you to know that this structure and that structure are the same thing. And I already gave it away. Are there any formal charges present in this molecule? Where are they? On the oxygen, what is it? A negative charge. Are you sure? He's positive. 2, 4, 6, 7 electrons are on this oxygen. It wants 6. It has 7. That's a negative charge. What about this oxygen? Normal charge? 0. It wants 6. It has 1, 2, 3, 4, 5, 6. Neutral. What about that carbon? Neutral. How many does it want? 4. How many does it have? 1, 2, 3, 4. Start doing this. When you see atoms, when you see molecules, just go through and just like beat the formal charge thing to death, because it's going to make you a lot faster at judging your structures that we're about to draw here. We're going to up the ante quite a bit. So I've got an oxygen with a negative charge. It is not pleased about it. But the oxygen with that negative charge isn't stuck there. I can move that negative charge around. And I have to introduce a concept that's going to be a little confusing here at first, but I want you to know about it. We're not going to use these so much right now. We will use them a bunch in a couple weeks. It's really pretty far down the line. But we use something called electron pushing arrows in organic chemistry a lot. We use them for a thing called a mechanism. You don't need to know any of that just yet. But what I'm going to do is I'm going to draw an arrow from the lone pair pointing towards this bond. What this arrow represents is an electron pushing arrow. There's a lot behind this arrow. What I want you to know right now is whenever I draw an arrow, I'm moving electrons from where the arrow starts to where the arrow is pointing. In my next structure, I'm going to draw an oxygen that only has 2 lone pairs, because that lone pair turned into what's going to be a double bond over here. If I have a double bond here, I'm going to break the octet rule for this carbon, right? Because this carbon has 2, 4, 6, 8 electrons. I'm about to give it another bond, which means I need to move electrons away from it. So I'm going to draw one more arrow from this bond to that oxygen. This arrow represents a bond turning into a lone pair on the oxygen. You do not need to know how to draw these arrows just yet. I'm going to draw them to keep your eyes on what's happening. Electrons are flowing from this oxygen up to that one. And the arrows, I think, are a great way of just keeping track of where everything's supposed to be. We will learn these formally later on. The next structure I'm about to draw here is connected by a new arrow. It's a double-headed arrow on each side, and this is called a resonance arrow. We use lots of different arrows, right? We have electron pushing arrows, yield arrows, equilibrium arrows, dipole moment arrows, resonance structure arrows. There's an arrow for everything in here. A resonance arrow represents a resonance structure. The next structure I'm going to draw over here is the same molecule, just rearranged a little bit in a different mood. So my CH3 didn't change at all. But now I need to account for these electrons moving around. I had a carbon-oxygen single bond on this side. Now I'm going to have a carbon-oxygen double bond. The reason for that is I took this lone pair and turned it into a bonding pair. So that's why I have a double bond here now. How many lone pairs on this oxygen? 2. There was 3 over here. I moved one of them. Now there's only 2. What's the nature of the bond between the carbon and oxygen up here? Single bond. The reason is I took a double bond and I moved it onto the oxygen. So now I'm going to just draw one line there. How many lone pairs should I put on this oxygen? 3 or 6 total electrons. The negative charge, the extra electron from this oxygen went up to that oxygen. This oxygen now has a formal charge of -1. The oxygen wants 6 electrons. It has 1, 2, 3, 4, 5, 6, 7. It has too many. This one wants 6. It has 2, 4, 5, 6. It's neutral. What this molecule did is kind of like a hot potato. I'm going to drop it. It's something lighter. I got a negative charge over here on this oxygen. I don't have a negative charge over here. This oxygen is suffering from that. So what it's going to do is pass that negative charge to the other one. So this one's now neutral and this one's negative. And then it's going to go, oh, that's not good. Pass it back. Back and forth. Back and forth. It's going to resonate. Anybody play guitar? Even anybody own a guitar? Sorry, different question. Anybody own a guitar in here? Everybody's, yeah, same thing. I have like 3 at my house. Can't play any of them. But when I clumsily interact with the guitar, if I pluck a string, what's happening is that string's sitting still, not making any noise. When I pluck it, it goes wah, 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 wah. It resonates. And that motion going back and forth is what makes the sound. When we say this molecule resonates, it's going back and forth between these 2 structures. Here's my stupid analogy I use. I think of resonance structures like personalities. It's the same molecule that just has a different attitude at that particular moment. I am an overly bubbly person. The person you see me right now, where I'm like jazzed about science, I feel that way generally about life. It's super annoying, I recognize. Occasionally I get pissed off. If you saw me on a bad day and you're like, Dr. Green's like not doing very well. If you went to like other people at MSU and you're like, Dr. Green is such a downer. He's like always so moody. People will be like, what are you talking about? He's one of the most like annoyingly energetic people I've ever met in my life. It's not that I'm always this way. I contain multitudes, but most of the time I'm pretty bubbly and upbeat. Occasionally, I go over to a different place and I'm like, no, it's no good. Still me. I just have different personalities along the way. Right? Same thing for these. That oxygen is still that oxygen. It just goes from a negative state to a neutral state, back and forth, back and forth. And it's a way that this molecule can deal with a negative charge that it develops. Resonance stabilizes a molecule. If you introduce a charge and you can resonate it, it makes the molecule more stable. For that reason, if I compare this molecule, which is called acetate, to this molecule, which is methoxide, I'm going to write these down because I'm saying it. You don't need to know the names of these. This molecule is called methoxide. This molecule is called acetate. If I wanted you to just generally compare the stability of methoxide to acetate, which one of those molecules do you think is doing better in life? Which one of those molecules is more stable? Acetate. They both contain oxygens with negative charges, but acetate can spread it out and share the love, the pain, among 2 different oxygens. Methoxide is just like, oh, it's hot, this sucks, right? You can't do anything with it. It's just hanging on to the hot potato. And for that reason, methoxide is more reactive. Methoxide is more likely to share its electron density with somebody else versus acetate's like, I'm not great, but I'm making it work, right? I have many rules to tell you about resonance structures, but I have no time to do so. And I've only ending class 30 seconds early, so now I owe you 1 minute and 30 seconds. I'm going to get those 2 minutes back. Have a wonderful weekend. I will see you all on Monday.